Hi, I'm Twisha, and I'm a master's student of Advanced Architectural Design at Carnegie Mellon University. And I welcome you to my thesis presentation, Aggregated Assemblies, which talks about revival and improvisation of indigenous construction practices through technological interventions in AEC. The project looks at intelligence in indigenous building practices and looks at how they can be given more visibility in the space of AEC and in the creation of new dialogues across disciplines and cultures. It lies at the intersection of the relationships between designers, builders, and fabrication related industries, and is directed towards architects and designers and presents to them a tool to help them integrate and explore the possibilities of these lesser known non Western local techniques in order to recontextualize them within design projects. A question that comes to mind is why should one look at indigenous building practices? And what does it mean to give them more visibility? Indigenous techniques generally source local materials for the construction and come with inherent environmental performance benefits that hold a lot of socio-cultural value. For the indigenous groups represented, it is a source of satisfaction from seeing contemporary design scholarship catch up with their time-tested practices. How does one ensure the preservation of local wisdom, which is not easily transferable, nor is very easy to write down in a book, and can easily die out with negligence? How can we as designers rebuild our knowledge base and generate new dialogues across cultures and disciplines? A part of my project depends on what definition of technology I'm basing my project on. I see technology as something to come into being. A designer or craftsperson is not the ultimate source of reality of what they are making. In fact, they are someone who help in this process of making. If we borrow from Heidegger, modern technology is often not seen as an aid for designing, but rather as something that is forced into the process of making. Technology within the AC industry addresses a limited array of techniques and only focuses on standard construction techniques, which are replicated all over the world. Automation and standardized construction is greatly affecting the learning and passing down of traditions and culture within indigenous communities, which poses a great threat to their identity. But it is also true that without the inclusion of technology, a craftsperson's impact remains limited with respect to the things they can physically do. So, how does one go about this inclusion without having makers lose their roles? How do we combine the intelligence of indigenous practice with the current technology? With this in mind, my project is posing the following overarching questions. Can indigenous construction systems be made more visible by augmenting them using computational design and technology aided construction? And can the improvisation of design and construction experiences reimagine the scope of architectural design? Have you heard of tubifittili? I'm sure most of you haven't. Tubifittili is a technique of tubular vaulting which originated in the Roman Empire and had gained popularity due to its ability to offer heat resistance and insulation while ensuring a lightweight design. It is a building technology that was born as a response to the scarcity of timber for scaffolding and an immediate need to provide for the growing population. Each wall structure is comprised of standard individual terracotta tube modules that are cylindrical and one end narrows to form a nozzle-like projection. This enables each tube to interlock perfectly with its neighbor. Any geometric variation at the micro level, that is the tube modules, greatly affects the structural feasibility at the macro level, the wall structures. Generally, grout is used to firmly position these modules in place, or the entire structure is plastered from underneath. An interesting part is that, according to a study that talks about terracotta vaulting with tubes, these modules are also among the first hollow bricks in history. While standard construction relies on mortar and gravity to secure layers of bricks in position, tubifittili involves the precise positioning of pots relative to one another in such a way that it's always building towards the global form of the structure. The keystone is a custom module that is hollow from both sides and holds subsequent courses in position. It is an in situ construction technique and observes a very typical structural family comprised of domes, walls, and arches. As standard construction modules started becoming more widely available, architects and designers chose to construct with them, and skilled labor with this background was also very limited. There were also nuances of working with this technique, such as producing so many pots and custom keystones, etc. So to summarize the primary features of QBPTD, we could consider the modularity with respect to the use of these interlocking pot modules, the flexibility in terms of arrangement of these pots based on structure that's being designed, which changes with complexity of structures, and finally, the precision or ability to nest or aggregate modules together with respect to one another. So how does one use current technology to best capture these primary characteristics? In the construction phase, technology-aided construction could have various outlooks, depending on the scale, context, and availability of labor and resources, and could vary from fully automated scenarios to hybrid environments, but could also include augmented manual construction, where humans would step in selectively where the technology fails to address some issues. As these scenarios facilitate the construction of complex tasks, seen in the first project by Ramazio and Kohler, where a robot is programmed to build a parametric wall, which is a rather complex task when it comes to manual building. And the second precedent also talks about augmented bricklaying in the augmented manual scenario. This project is from ETH Zurich and highly depends on like the implementation of augmented reality in construction scenarios. The third project is from ETH Zurich, which is a hybrid scenario where the human selectively jumps in the process of uh, tasks that the robot is not programmed to do. For the scope of this project, as well as considering the current COVID scenario, I would be looking at the augmented manual construction scenario. For the two parts of the project, I have been looking at ways in which construction workflows are rethought using computational design and fabrication tools. In this project that deals with Inca stone construction, Brandon Clifford's studio, Matter Design, looks at how current technology can be combined with the features of the Inca stone construction to create new structures comprised of repurposed stones. Another project from Tom's University aims at creating wall structures using irregular foam bricks and talks about the integration of augmented reality and a human-computer collaborative framework to reduce accumulative errors that arise while working with freeform buildings. Building upon these precedents, how does one really choose the right platform and tools for digitizing QBT? So the scope of my project presents designers with a toolkit that extends their understanding of technologies that can be integrated and recontextualized in their design practices. To accommodate the modularity and flexibility required while working with TUB a computational backend with an intuitive user interface that captures the features of the technique is proposed. Along with that, a complementary mixed reality aided workflow that enables a maker in the precise placement of modules in a prototyping setup is also proposed. So how exactly might computational design and mixed reality be used to aid a designer in utilizing QB Let's have it. So here is the first part of the project, the computational backend. Back when the Romans built structures using QB they for sure did not pass on working drawings to masons for construction, as this technique relies highly on the tacit skills and intuition of these skilled craftspeople. But that's not the situation now, and there needs to be a tool for architects and designers for being able to use this design in the current scenario. The methodology for this computational backend comprises of deriving the component and structure details from literature and building upon them to set up the design parameters in the design environment that is built on top of Rhino and Grasshopper. Custom features pertaining to TUB are added using Grasshopper as well as scripting in Python. Finally, a intuitive user interface is built on Human UI, a plugin for Grasshopper. The structure thus designed is then brought into another platform on Unity, which enables the mixed reality aided workflow to be deployed using the hardware's Oculus Rift and the Z Mini, which aid the maker in prototyping the structure design. The design considerations occur at three main stages: definition of design context, definitions of component details, and setting the constraints and goals for the final structure. A combination of parameters defines the features included in the final structure. These could be user-defined, such as the drive surface or the module preferences, etc., or system automated, meaning the user would have less or no control over the parameters. And this might include the performance calculating features such as the structural performance or the radiation study or for this structure. Or it could mean hybrid parameters, which means the user would have limited options to choose from as defined by the tool. The algorithmic breakdown of this problem involves identifying the quantifiable features and limitations involved in working with this technique. It includes understanding the range of aggregation modules and their limitations with respect to the maximum and minimum angles at which they can aggregate. Building upon the same approach, with every aggregation, the range of the module changes relative to the previous module placed. Now, with this algorithmic logic in mind, there could be two design approaches. The bottom-up approach, which starts with a selection of module at the micro level, followed by geometry aggregation to form the final structure, or the top-down approach that starts with a user-defined macro surface over which the aggregation takes place. Let's look at my attempt at the bottom-up approach. I started by defining the details for pot modules and used an agent-based modeling approach for geometry aggregation. This resulted in global structures that did not seem to work perfectly well with the system. Plus, the user did not have significant control over the kind of geometries produced. And nor is the system parametric. This process is stochastic in nature and not deterministic. Because of these reasons, I started looking at the top-down approach, where the designer defines the macro surface and has parametric control over custom features of the overall structure. Based on the features of modularity and flexibility that need to be facilitated, the design workflow consists of three phases. The first part includes the user having to upload a surface geometry, which would be the macro level form of the structure. The user has ability to control the properties of the surface. This phase also involves surface subdivision of the structure and the ability to adjust the seams thus produced. The next part is the custom module definition, which parametrically informs the aggregation on the structure level. The last phase involves definition of apertures based on either patterns generated during aggregation, but can also cater to custom openings that require to upload an extra seam on the surface. Gaps in sparsely aggregated structures can be reduced by populating with more pots based on the same algorithmic logic. Once the user is satisfied, he could export the structure to be further worked on with the prototyping workflow. Here is a visual representation of the workflow in the first phase, where the structure is uploaded, subdivided further, and then aggregated. It also is worth noting that the subdivision for all depth surfaces works differently, as seen in the case of domes with radial subdivisions and walls with quadrangular. Custom seam control is a useful feature of the tubifiterium, which is useful when a complex surface comprised of several subparts, as seen on the precedent on the left, is to be worked with, where each surface may require a separate direction for aggregation. Specifying the type of structure might also be necessary, as it might talk about how the structure is aggregated. In the case where the user wants to include radiation studies, specification of location would be required. While these phases may seem linear in nature, one might always be able to go back and update the previous preferences to analyze design variables and their effect on the form produced. Literature, as well as my design intuition, helped me explore the taxonomies of surfaces that could be considered as drive surfaces for this tool. The results from my experiments worked fairly well, where I tried working with simple domes and walls and also some complex structures that are comprised of more than one drive surface. But the tool at this current stage takes a lot longer to process more complex geometries. This is a demo of the Twisha design tool where the user uploads a surface, specifies the type, and also has ability to adjust the structure properties. He then can also select from preset modules or define his own module. Also, there is an ability to uh, control the curvature of the pot. Once satisfied, he can save preferences for using in his next design iteration. The form aggregation comprises of defining the opening preferences. A user can choose what kind of opening he wants and also indicate whether the gaps in the structure need to be reduced. Once done, he can generate the form and export the geometry from there. So the aperture and opening preferences are limited considering the limitations of this technique, and they are based on two. There could be two ways of including openings in like while building in this technique. They could either be based on a fixed pattern application logic that involves the knocking off of pots where openings are preferred. And in the case of custom scene preference, an added structural member appears on the design while the geometry is aggregating. The next part of the project is the mixed reality assisted construction prototyping setup. Cubifitili is a non-intuitive technique as compared to standardized construction processes that we are familiar with and requires an added level of guidance while placing the blocks in position. Here, the attempt is to create a suggestive framework that indicates the user about precise placement of modules relative to one another, as seen in this video. While working on this demo, uh, the user was prototyping a part of the design she made in the design tool. She decided to go against the suggested workflow because it did not seem to work very well with the structure she had designed and envisioned in the tool, an irregular arch profile. This was also challenging. This was also a challenge to the design environment I had created. In this demo, the user actually takes the range of deflection of each pot as a complementary factor in the creation of structures. And while this approach may seem to work and seem better than the suggested workflow, in reality, when the pots are mortared in position, it would definitely require the user to place each pot in position precisely. So, in my effort to unconceal these lesser known practices, I uh, propose this framework, which involves uh, a computational backend and front end, which caters to the needs of modularity and flexibility, and a mixed reality prototyping environment that helps in the precise precision required while working in this technique. I understand how these characteristics of 2D Fitili construction can be digitized uh, by breaking down the process algorithmically and how it can be presented in the form of a tool to a designer. In the process of working on this project, I always wondered how one could possibly build upon this pipeline and scale up workflows to be deployed on site at relevant locations. And again, it's not just about this one technique being given more visibility. So, how do we as designers create more such frameworks to contribute towards preserving local wisdom, rebuild our knowledge base, and generate new dialogues across uh, disciplines and cultures? Because in the end, it's not just about this one building practice that I'm looking at. There are so many other communities waiting to be empowered and recognized. Thank you.